So the first thing is this. This theorem is super important. Because what this theorem is saying is this. It's this idea, there's no smallest, and you want to write this real number. You know this already. No smallest real number can exist.
Yes.
Very good. So let's look at it for a second. So we got the real number line R here. And I missed something very important. That's what? No smallest positive. So positive real numbers do not include 0. No, 1. So we're going to put 0.0001. So we're going to put this here. And then this is whatever. Now, what did you do the other way? Let's put that other way.
It's not included.
Yeah, then it kind of divides it. Yeah, very good. And then 0 is 0. Give me, I'm going to find m. This is going to be my smallest real number. And between this and this is between 0 and m, which was our candidate smallest positive real number, are infinitely many smaller real numbers. Yes? That being no.
That is a fact.
That's a fact. Okay, so let's remember that fact. So then it says is that if you have this, A is greater than or equal to 0, and A is a real number. And what you want to prove about A is that it is a very, so you want to say that A is actually, so it says, it's greater than and equal to. What we want to show is so they give us this and we want to show
That A is greater.
or that, show that A is actually equal to 0. Because we wanted A to be a very, in fact, the smallest positive real number. But in fact, that is not possible. In fact, so if we want to show that show that A is actually 0, as in this, all we have to do is, and this is a very important to do, is to show that A is less than a very, I can't say this word, very small epsilon. If you can do that, then A equals 0. All you have to do is show that A is less than another very small positive number, and that will imply that A is actually equal to 0. 2.1.9, and it's from the Bartle and Sherbert book theorem. If A belongs to the real numbers, is such that 0 so what's happened here is that the conditions are A, these are the two conditions. A belongs to R, to the set of real numbers, and A is smaller than the smallest positive real number that we can think of, but it's still supposedly bigger than 0. If this is the situation where, right, remember we said, if we have this condition, and then we can show this, then we can say that A equals 0. So this has all of the ingredients. So if this condition is true and this condition is true, so then we got two conditions on the first line, then actually I'll just add upon every here. So for this thing comes with for every conceivable positive epsilon. And so these are two conditions. Conditions. Then, and here's our principal statement. Then A equals 0. Or the result. If those two conditions are true, the top ones, this one here, and this one, then we can assert that A equals 0. So, what did I do? Oh, the proof is here. Okay, so suppose, obviously, I hate these proofs, but this is a proof. Suppose, to the contrary, so it's a proof by contradiction. It's so hard to work with real numbers, all the proofs are like that. They use contradiction that only suppose to the contrary that, and I think I added this, A is greater than 0.
Okay.
Because over here,
Yeah,
it says equal to.
yeah,
So that allows us to say A equals 0. Here we're saying even, so when we do this line here, move this here. When we do this line, we are basically saying that even if we find that A is smaller than an epsilon, it's not going to equal 0. A will always be the smallest possible, smallest
positive number.
positive number, which is not true because we know that the smallest positive real number does not exist. Very good, sir. So then all we have to now do is we're going to find something even smaller than, right? It says every epsilon. We're going to find another. We're going to make A less than even smaller epsilon than this one, pushing it towards the, okay, to the left. All right, so let's see. Here we have a line. Okay, and we have 0. We have A, which is to the right of 0, and all of these guys are smaller than epsilon. A is smaller than epsilon, so this is kind of like that, right? This is.
I had that drawn earlier
Mhm.
while you were typing or not, writing, and I thought it was wrong.
But it was correct.
Yeah.
See? You getting it, or I'm getting it wrong, so.
Yeah.
It's either case.
We're both working out.
Because remember, line is leading the byline. Then, so right now, A is smaller than this guy. What if we make A, so the theorem was if we take another epsilon, an epsilon naught, the small o, and we define this, and they put two dots and an equal to, define it to be half of A. So the length A, half of length A. So now our epsilon is actually smaller than A.
The colon and equal sign is to define.
Define. So this means equal,
Yeah.
and dot means to define.
What else you can use?
We have. So we have, rather than this, we have this. Oh, okay, sorry. No. We have. So this is.
0 is less than A. The A is greater than epsilon.
Yes, sir.
Yeah.
I was getting confused. Because this is, so A is here, A is bigger than the smallest positive number, and it's still bigger than 0. So, right? A is still bigger than 0, which is what we were. Okay, so if that is the case, therefore, what's happened is we have found an epsilon that is not bigger than A. We have found an epsilon where A is not smaller than that epsilon. This condition has been, because we said this condition got killed.
Yeah.
Okay, so therefore, contradiction. Therefore, we can say that, therefore, it has become that it has become false.
Yeah.
Because it is false that A is less than epsilon anymore. Because it's every epsilon, right? Every. Including, it should have been smaller than this guy. Because what we just did was, we showed that between A and 0, there are smaller positive numbers.
Yeah.
Infinitely many more.
See, this makes total and complete sense. Algebra doesn't.
That is weird. This is way harder than algebra.